Okay, so this is the last section in section 4.9. We're talking about antiderivatives, which are a crucial topic, crucial concept that is going to be used throughout the rest of calculus, essentially. And not just calculus 1, you're going to use it all throughout calculus 2, and you'll continue using it in calculus 3. But it's very, very important for what's coming up in chapter 5, which will kind of set the stage for calculus 2, basically. So we've been spending a lot of our time worrying about derivatives. Chapter 3 and chapter 4 primarily, end of chapter 2 as well. We introduced the derivative there. The antiderivative is kind of like an inverse of that. It's sort of the opposite. You know, and when I say inverse, what I mean is like an inverse operation. Plus and minus are inverse operations. If you add 8 to a number, subtracting 8 from the result gets you back to where you started from. It sort of undoes what you did. Multiplication and division are inverses of each other. Squaring a number and square rooting a number, those are inverses. So an antiderivative is like that to a derivative. But for a more accurate definition, let's talk about that here. So a function capital F is called an antiderivative of lowercase f on some interval I if big F prime of x is equal to f little f of x for all x in that interval I. In other words, if you have a function little f, an antiderivative is a function whose derivative is the function that you started with. In other words, we're not taking the derivative of little f. Instead, we're trying to find a function whose derivative is little f. Okay, so to illustrate an example, let's look at this. Find 3 antiderivatives of f of x equals 3x squared. Well, this looks super familiar to me. I've seen this pop up plenty of times, and it shouldn't take a whole lot of work to determine that one antiderivative you could come up with is x cubed. And if I wanted to verify that I got that right, I would take the derivative of my answer and make sure that I got little f of x. Checks out. The power rule would tell me that this is an antiderivative. But there's other antiderivatives of this function. Let's call this one g of x. X cubed plus 1, for example. This is also an antiderivative of that. And I can verify that very easily. When I take the derivative of this, the constant goes to 0, and I get 3x squared again. Here's another one. H of x equals x cubed minus 100. Same thing. If I take the derivative of this, I get 3x squared. So there a couple of things worth noting here. Antiderivatives are a little different than derivatives in the sense that if I have a function, a differentiable function, it can only have one derivative. So if I were taking the derivative of this function, the derivative is 6x. It doesn't have any other derivatives. But a function can have several antiderivatives. In fact, it's not that hard to see that I can come up with an infinite list of antiderivatives here just by changing this constant that I'm tacking onto the end here. So a better question is, are there any other antiderivatives to this? Meaning, are there any antiderivatives of this function that look like something other than x cubed plus a constant? And the answer is actually no. All antiderivatives of this function will look like x cubed plus some constant. So, and by the way, if you're looking at this and you're saying, well, but that's minus a constant. Well, it's also plus negative 100. So I'm not wrong to say that this is x cubed plus a constant. In section 4.2, we actually proved this. We just weren't using the terminology of antiderivatives. We used the mean value theorem and Fermat's theorem, which, remember, we covered a lot of theorems back in that section, to prove this. We proved that if a function has, if two functions have the same derivative on some interval I, then they must differ by a constant. You'll find that in one of these red boxes in section 4.2 if you go back and look. That means this: if capital G of x and capital F of x are both antiderivatives for the same function, say little f of x, or equivalent, then they differ by some constant c. G of x minus f of x is going to equal some constant function c. Or equivalently, g of x is equal to f of x, capital in both cases, plus c, which is kind of what we're seeing here. So we're going to state that as a theorem. If capital F is an antiderivative of little f on an interval I, then the most general antiderivative of little f on that interval I is capital F of x plus c, where c is any arbitrary constant. Okay? And so what we're going to do is use this to find the most general antiderivatives of several functions here. And right now, it's going to be trying to match up what we know about derivatives and sort of work it backwards in our mind. And then I'm going to give you a table of antiderivatives that you can use for reference. But here we have f of x equals x to the fourth power. I need an antiderivative for that. Now, if I were taking the derivative as opposed to the antiderivative, then I would be using the power rule. What does the power rule tell me to do? The power rule says to subtract this exponent by 1. So 4 minus 1 would be 3. And then multiply by this exponent. So 4x cubed is what I would get. Notice I'm multiplying by the power and then subtracting 1 from the power. If the antiderivative truly is the opposite of a derivative, I want to do the opposite of those steps. So rather than subtract 1 from my exponent, I should be adding 1, giving me x to the fifth. And instead of multiplying by this exponent 5, I should be dividing by that exponent 5. Now, especially as you're getting used to finding antiderivatives, you should be verifying that you have the correct answer. And the way that you do that, like before, is you take the derivative of what you got and see if you got the same, see if you got your original function back. So the derivative of x to the fifth over 5 is x to the fourth. That's easy to verify. So we got it. But it's not the most general antiderivative because I didn't put this plus c here. Okay? And that's what this theorem is telling me. Whenever I find an antiderivative, I have to include that plus c if I'm looking for the most general antiderivative. Let's do another one. This function is essentially the same as this one, except I've generalized it. Instead of the exponent being a 4, I have an n. So I want to use the same technique that I did before and add 1 to the exponent and then divide by that exponent. That would give me x to the n plus 1 power over n plus 1. And again, verify that this is in fact the correct antiderivative for this by taking its derivative and getting x to the n back. Don't forget to put the plus c. Now, why did I say n is not equal to -1 here? Well, we're going to deal with that over here because 1 over x is the same thing as x to the -1. And we know that that's kind of a special function that comes out a little bit different. So we'll get to that. Okay, what about this one? Little f of x is equal to secant squared of x. Can you think of a function that has secant squared as its derivative? Hopefully you can. Tangent of x. Its derivative is secant squared. So that means tangent is an antiderivative of secant squared. Plus c gives me the most general antiderivative. Okay, finally we have this guy. Can you think of a function whose derivative is 1 over x? I sincerely hope that you can. The natural log of x does. Now, you may not remember this, and I would encourage you to go back to chapter 3 where we found the derivative of the natural log function to refresh on this. But we found that the natural log of x is not the only function whose derivative is 1 over x. The natural log of the absolute value of x has 1 over x as its derivative as well. And the difference between this function and the natural log of x is that this function is defined for negative values as well as positive values, whereas the natural log function is only defined for positive values. So when dealing with antiderivatives, we use the absolute value here because it gives us a better function, a function with a bigger domain than the natural log function would. And it still gives me a correct antiderivative. Plus c gives me the most general antiderivative. Okay, so here's a table of antiderivative or antidifferentiation formulas. We don't need to derive all of these because we essentially have already. They're just the derivative formulas in reverse. So for example, We know that if you take the derivative of a constant times the function, it's a constant times the derivative. The same thing happens with antiderivatives. If I want the antiderivative of a constant c times the function f of x, it's c times capital F of x, where capital F of x is just any antiderivative of little f of x. They also have this additive property. I could replace this plus with a minus here, and the same thing would be true. We derived this one on the previous page. X to the n has as its antiderivative x to the n plus 1 over n plus 1. We did this one as well. 1 over x has the natural log of the absolute value of x. The exponential function is its own derivative, so naturally it would also be its own antiderivative, right? And then you can kind of look through the rest of these and see that they're really just the differentiation formulas in reverse. So let's take a look at another example. Find all functions g of x such that g prime of x equals 4e to the x plus 5x cubed minus root x over x squared. So in other words, we're looking for antiderivatives of this, because I'm looking for functions that have this as a derivative. I'm not taking the derivative of this. I want functions whose derivative is this. Okay? So again, it's just an antiderivative. Now notice, it's a sum of two functions, so it looks like this. If I want the antiderivative of a sum of two functions, it's just the sum of antiderivatives. So I can take the antiderivative of each of these separately. And this is a constant times an exponential function. I know that I can leave the constant alone and just take the antiderivative of my e to the x here. But e to the x is its own antiderivative as well. So g of x can be written as 4e to the x. Okay? And 4e to the x is going to be my first term. Okay? And verify that if I took the derivative of 4e to the x, I get 4e to the x back. Now this guy, it may be tempting to just differentiate all of these terms separately and leave it as a quotient, but you know that you can't take derivatives that way, right? Like if I said take the derivative of this term instead of antiderivative, oh, sorry, 1 second.